Welcome back to another exciting chemistry lesson. In this lesson, we are going to look at equilibrium. Now we have a graph, concentration versus time, and we have specific time frame on this reaction. And this is the reaction that we are looking at. Notice how we have two reactant producing a product. And this right here, we know that this is a reversible reaction. And a reversible reaction, basically, the forward reaction where the reactant are forming the product, and then the product is going back the other opposite direction where it decomposed or it reacted with itself to make the reactant again. So we call that reversible reaction. So they're going back and forth, and this is happening at the same time, okay? So what is equilibrium? In order to understand that, let's look at this graph. Initially, if you notice right here, the product, SO3, we don't have any product, but we have reactant right there, right? So over time, the reactant reacted and combined to make the product. So as you can see here, this concentration of reactant decreased where the product increased, but to one point, because this is reversible reaction, that means the product going to make reactant going to make the product. So it happened at the same time, but until it get to one point, that you have enough reactant, you have enough product, that both of them are a fair amount. So what does that really mean? Well, in order to understand that, we're not looking at the concentration, but we're looking at the rate. So initially, when we have zero product, the rate of making the product is a lot higher, right? Where we pretty much almost have nothing in terms of making the reactant from the product. So in terms of chemical equilibrium is occur when the rate of forward and the rate of reverse are the same. They are equals, okay? Now, that means there are no changes in the concentration of reactant. There are no changes in the concentration of product. So if we look at this graph right here, at T3, we see that this is not the same, but right away at T1 and T2, for the rest of it, until we have some kind of disruption, it is at equilibrium pretty much forever. See how the line is flat? That means the concentration doesn't change anymore. So the concentration of this reactant and this reactant stay the same, because as it's making product, the product is also making the reactant in the opposite direction. So keep that in mind. Equilibrium occurs when the concentration in terms of rate of forward and the rate of reverse is the same. So therefore, you will not see any changes in the concentration. Now let's look at equilibrium in terms of equilibrium constant, and that is represented by the letter K. Now equilibrium constant relates the concentration or the partial pressure. So notice how we have Kc, that's for concentration, and Kp is for partial pressure. Relate the reactant and the product at equilibrium, and that's the key. The K is for equilibrium at any given temperature and pressure condition out there, okay? And that's the key. Where, what if a reaction, now what if the reaction is not at equilibrium? How do we relate reactant and product that are not equilibrium? Well, we have something called reaction quotient. Well, quotient is basically division, right? Or fraction, think of that way. And it relates the concentration or partial pressure, how we have Qc for concentration, Qp for partial pressure of the product and reactant. I just changed the word, okay? They're all the same thing, okay? At any point, and of course, it could be at equilibrium as well. So Q is for any point at any time for that particular reaction. So what does that tell you? Well, if K is for equilibrium, if Q is equal to K, that means it is at equilibrium, because again, K is for equilibrium. So now let's learn how to write the quotient or the equilibrium constant for a reaction. And all you have to do is very straightforward. You need to balance your chemical equation first. See, notice how we write internal A, B, C, D, right? And notice how we have this right here, A, B, C, D. Those are the coefficients of a balanced chemical reaction. But there is one catch, and that is you do not include any solids or liquid in the quotient or the equilibrium constant. So let's do an example problem, how easy this is. Well, of course, the first thing is you have to balance the chemical equation. Well, in this case, the equation is already balanced for you. You have 5, 2 and 3 is 5, and then we have 4 plus 1, that's 5. So again, this is already balanced, and we gave you the answer here just to show you and so how we type this on a computer. And that is, we just use the caret symbol to indicate exponent. So let's do this. See how we have internal concentration? For partial pressure, it would be like this. If I'm writing in terms of QP, all I have to do is just partial pressure of C, partial pressure of D, divided by partial pressure of A, partial pressure of B. You see that? We just don't use the concentration bracket, but we use P for partial pressure. So the same concept, okay? So let's look at this practice problem. Here we have equilibrium constant for concentration, reaction quotient for concentration. Here we have for partial pressure, and we have for partial pressure as well. In this case, we're dealing with aqueous solution. We're not really dealing with pressure. And A is for not applicable, so we don't really have it, okay? So let's focus on this one. For equilibrium constant, again, just product over reactant. So I'm just going to write that out over here for you, okay? If you don't remember, just product over reactant. There you go. So look at product. We have NH4 plus, OH minus. So, and they don't have a coefficient, so we assume it's just going to be 1. So NH4 plus, okay? And we don't have coefficient, so therefore there's nothing there. Time OH minus divided by the reactant. Well, in this case, this is liquid, so we don't care. And NH3. That's how easy it is. If there is a coefficient, it will go up here. Okay? Now let's try another problem. Again, we are writing equilibrium constant or reaction quotient in terms of concentration or pressure. And again, we always write products over reactant. So here we have product over reactant. And we ignore solid and liquid, okay? So let's look at this. Let's start with our product. Well, our product, this is a solid. We don't really care. And here we have oxygen, so it's O2. But look at that. That right there is a coefficient, so that go right there. Now let's divide by our reactant. Oh, look at that. Our reactant is solid, so we don't have anything on the reactant side, which we assume is 1, but anything is 1 is by itself. So we don't have anything for the reactant. So our answer is pretty straightforward. KO2 3. Remember, we use a caret symbol like that. And for QC, it's the same thing. Let's look at KP. Well, all we have to do is just remove the concentration and convert into partial pressure. Partial pressure of O2 to the third power. There you go. And for QP, it's the same thing as well. So that's how easy it is to write an equilibrium constant or your reaction quotient. Just be careful. We don't include solid and we don't include liquid. Eventually, we are going to give you the values and you're going to substitute it in and solve for K and Q as well. And if you have any question, please take a picture of your work and put it in a forum and we will do our best to support you. And we'll see you next time on another exciting chemistry lesson.